This is 4.3 Algebra 2, and because this is a long lesson, I'm going to break it into two parts. So for Thursday, you only need to watch the first part. If you have time, it's great if you can watch both. Anyhow, section 4.3 is on logarithms, and this is brand new stuff. The main thing to remember about logarithms is that they are exponents. That's like the overall main idea. Logarithms are exponents. We have a question, why are you drumming on your algebra book with two big sticks? So you could probably guess maybe from the title, it might be something like this, because we're studying logarithms, which are exponents. And we'll be doing a fair amount here in this section. They're going to learn quite a bit about these things. So we're going to learn what a logarithm is. We already know it's an exponent. There's a difference between the common log, and then we're also going to look at logarithmic functions and graphing those. First question we have is, how many times would you have to double $1 before you had $8? Well, that's a fairly simple question. We could do it by just by thinking about it. You start with $1. If you double it once, then you're going to get $2. If you double it again, you're going to get $4. And if you double it again, you're going to get $8. So that took 3 times in order to do that. Well, since this is an algebra class, we also might wonder, is there an equation we could have used to describe this relationship? And indeed, when you double things, it's actually exponential. It's exponential growth. And so we could use one of the exponential equations. And the one we're going to use is y equals a times b to the x that we looked at a couple sections ago. We know that the a is the starting value. So we started with $1. So the 1's going to go in for a. And b is the base. When you double, the base is 2. If you were tripling, the base would be 3, and so on. It says how many times would you have to double it. The x is the number of times, and the y is the final amount at x times. So the final amount in this case is 8. So if I simplify this a little bit, 8 equals, I don't need the 1 because 1 times 2 to the x is still 2 to the x. And I get this equation. So far, when we've tried to solve something like this, well, we had ones that were much more complicated and we had to use a calculator. For this particular one, you could think about it, 2 to what power equals 8? And, well, we already know it's 3, because 2 to the third is 8. Notice the 3 is an exponent. That 3 is actually a logarithm. And we'll see here in a bit, we can rewrite this equation. Actually, maybe I'll just go ahead and show you now. Why not? We can rewrite an exponential as a logarithm. And the way it looks is you write log, and then you write the base. The base of the logarithm is the same as the base of the exponential. So the base of the exponential is 2. So we put 2 down here. And there's going to be a number right here. Log base 2 of whatever goes in here is going to equal the exponent. This is going to be the exponent, because remember right away I said logarithms are exponents. So in this case, the exponent is x. And so that means that the 8 has to go here, because that's the only place left for it. Base is here. Think base down low, it's down below. That 2 is the lowest number in this equation. And this is the base here. And this is the exponent. Also, if you have a logarithmic equation, like I have over here on the right, it goes both ways. This arrow is double-sided. So you can write logarithms as exponentials. You can write exponentials as logarithms. It's just two different forms of representing the same relationship. I can't tell you enough how important it is to understand that logarithms are exponents. because that way you'll always know that your logarithm equals your exponent. Your exponent will be over here on the right-hand side. So I got a little ahead, but you know, that's basically, I mean, that's okay. We're learning this in this section anyhow. Okay, let's do this next one. This time it says, how many times did you have to double $1 before you had $512? So I'm going to put that into that equation I had earlier, the y equals a times b to the x. This time the final y value is 512. The initial y value is still 1. We're still doubling, so the base is still 2, and the x is the unknown because we're trying to find out how many times. Let's clean this up a little and write it like so. Okay. So we're wondering 2 to what power equals 512? And at this point you would have to guess and check. And I'm a little rusty on I kind of think I know what it is, but because 2 to the 10th is 1024, so it's probably 2 to the 9th. It is indeed. So 2 to the 9th is 512. So at this point you would have to guess and check because we don't have a way of solving it yet. We're going to end up using logarithms to solve because we're solving an exponential equation, and we solve equations by undoing by using their inverse, and exponentials and logarithms are inverses of each other. So you can see that's why we learned about inverse functions in the previous section, so that you can understand that exponentials and logarithms are inverses of each other. So in this next statement here in these beautiful colors, we have what I showed you on the previous slide, how exponentials and logarithms are related. So notice again, if the base of the exponential is going to be the base of the logarithm. So the b is the base, and that's the base. And again, logarithms are exponents. So this whole logarithm has to equal an exponent. The x has to be the exponent. Sure enough, if I look over here on my exponential, it is the exponent. And then there's nothing, there really isn't a name for the a, but the a goes right here. Once you figure out the base of the exponent, there's no other place for it to go. It has to go there. We will be switching back and forth between these two forms. In fact, here's our next example. So in this chart, they are giving us on the left exponential equations, and on the right we are going to write them in logarithmic form. So I know it's going to be log, and then there's going to be a base. So look at the exponential. What's the base? It's 3. So that means 3 goes down here. And then we know that the logarithm is going to equal an exponent, so the exponent's going to go over here on the right-hand side. The exponent is 5, and that means the 243 has to go right there. Okay, I would say do these on your own. Pause the tape, do these on your own, and then return, and I'll be doing them. Okay, so this one's going to be log. The base is 25. The exponent's 1/2, and that means the 5 goes here. By the way, another way to think about this is you can read this, or you could think about it as log base 25 of 5. Oh, by the way, that's how you read these. You say log base 25 of 5 is 1/2. And another question you ask yourself, or you would say 25 to what power equals 5? That's how you read log base 25 of 5. That one's a little harder to think about. Let's do it again on this next one. So this is going to be, start off with log. We write the base. The base of the exponential is 10. It's going to equal the exponent, which is 4. And then the 10,000 has no place to go but right there. So if I wanted to describe, say I was going to talk about log base 10 of 10,000. The way I would read this, or the way I would think about it is, well, I'd say it's log base 10 of 10,000. it means 10 to what power equals 10,000. I highly recommend writing that down because that's key to understanding what logarithms are. Remember, logarithms are exponents. What power? That's an exponent. That's what you're trying to figure out. Of course, in this problem, they already told you, you already knew it was 4. But 10 to the 4th is 10,000, right? Okay, the next one, log, the base is 6, the exponent is -1, and the 1/6 goes there. And the very last one, log, the base is a, the exponent is b, and the c would have to go there. Okay, we've completed the first table. Same question. So again, do these on your own, and then you could check back with me. So this one, we're writing logarithms, log, base 9, and then the exponent's going to be on the other side. The 2 will be the exponent over here on the other side, and we're taking log base 9 of 81. So log base 9 of 81 equals 2. Or in other words, 9 to what power? You would think, like if you were just looking at log base 9 of 81, let's say you didn't know it was 2, you would ask yourself 9 to what power equals 81? And you would know 9 squared is 81, so that means this is equal to 2. So see how the logarithm equals the exponent. What power? That's the exponent. Okay, log base 3. And at this point, you know, hopefully you can see, I mean, I'm always putting the exponent over here first, but you know that the 27 is going to have to go there once you do these enough. And then this one's going to be log, the base is x of 1 equals 0. Exponent's over here on the right. Okay, we accomplished that one. Now we're going to go the other way. Now we're given logarithms and we're going to find exponentials. So the base, exponentials are in the form of, or they have a base, so the base is 9. 9 raised to the exponent. This number here is the exponent. So it's 9 to the 1 equals, and then this number is going to go here, 9. So the base is that 9. The exponent's right there. Okay, we'll do another one. 2 to the 9th is 512. The next one, the base is 8, raised to the exponent, which is 1/3, equals 2. 4 to the -2 equals 1/16. b to the 0 equals 1. You can check these too. Is b to the 0 equal to 1? Yeah, any number raised to the 0 is 1. Is 4 to the -2 equal to 1/16? Yeah, because remember 4 to the -2 is the same as 1 over 4 to the 2, which is 1 over 16. 8 to the 1/3, we haven't talked about those yet. It happens to be the cube, well maybe we have. We've talked about cube root. 8 to the 1/3 is the same as the cube root of 8. What number times itself 3 times equals 8? And sure enough, it's 2. Sorry, I'm yawning. Okay. Same deal. So do these on your own and then check back with me. Okay, so now we're writing in exponential form. The base is 10, the power is 1, or the exponent's 1, and it equals 10. Sure enough, 10 to the 1 is 10. Here, the base is 12, the exponent is 2, and it equals 144. Yep, true statement. Next one, oh, blank. So let's see, let's make an x there because we don't know what it is. Base is 1/2, exponent is x, it equals 8. So what do you think that would be? Try it on your own, and then I'll tell you. So this one takes a little bit of creative thinking. You're raising 1/2 to a power, and you're getting a number larger than 1. I'm trying to think of how would I explain this without giving away the answer. Well, let's say it was 1/2 to a positive x. Like just say, well, since it's 8, let's try 3, because 2 to the third is 8. Let's just say you tried 3. You're just guessing because you've never seen something like this before. So if you had 1/2 to the third, that's the same as 1 to the third over 2 to the third, because the 1/2 is in parentheses, so the power applies to both. 1 to the third is 1, 2 to the third is 8. So we get, if we raise 1/2 to the third, we get 1/8, but we want it to be 8. We want it to be the reciprocal of 1/8. So a logical guess would be -3. 1/2 to the -3. And there's a really long way to figure this out, and there's also a fast way. Of course, I want to do it the fast way. If you would have probably learned this in Algebra 1, but you probably have forgotten it. When you have a negative exponent, when you have a fraction raised to a negative exponent, you can do the reciprocal of the fraction and then change it to a positive exponent. So it's a little shortcut. And you can see, lo and behold, of course, it's 2 to the third, because it's going to be 2 to the third over 1 to the third, which is 8 over 1, or just 8. So remember, if you have, let's make up a little rule, n over m to the negative x, I'll say. That's the same as the reciprocal, m over n, to the positive x. It's a really handy property. It saves you a lot of time, because you don't, doing it by hand, like doing it the long way, you'd have to write, if you had this and you wanted to do it the long way, you'd have to do 1 over 1/2 to the positive 3, and that takes a lot more time and work, because then you'd have to do 1 over 1/2 cubed is 1/8, and then you'd have to do the multiply top and bottom by the reciprocal, and that would cancel, and you would get 8 finally after all that work. Let's see what we got under here. A logarithm is an exponent, so I've been saying that over and over, how important that is to understand. And so the properties for exponents also translate to logarithms. So let's look at some of these. This first one, I'm going to do it down here so I have room to work. Log base b of b, and it equals something I don't know, so I'm going to make that be x. Okay, to figure this out, let's rewrite this as an exponential. So the base is b to the exponent, which is x, equals b. Well, now I can look at that. Oh, what does x have to equal? Well, it has to be 1, right? b to the 1 is b. So that means 1. B to the log base b of b is simply 1. Oh, and over here we've got exponential form, so that's what I just wrote. B to the x equals b. And an example would be log base 7 of 7 is 1. Because if you rewrote that as an exponential, down here, 7 to the 1 is 7. Okay, next, let's do this one. Log base b of 1 equals some unknown number, x, we're trying to find. Okay, we're going to put that into exponential form. The base is b, the exponent is x, and that equals 1. So b to what power equals 1? 0. So log base b of 1 equals 0. In here we'll put the exponential form. B to the x is 1. And an example would be log base, I'll make up one. How about 9? Log base 9 of 1. We know that that equals 0. And you can check it because 9 to the 0 equals 1. Yes, that's true. Anything to the 0 power is 1. Well, we've made some pretty good progress. Let's see. We've got a logarithm with base 10 is called a common log. So the thing about common logs is instead of writing log base 10 of, well, I've got a 5 here. Instead of writing that, because that's what it is, that's a common log, we just skip the 10 and we just write log of 5. So anytime you see log of a number and there's no base, it's understood to be 10. If there's no base down here, it's understood to be 10. And it's a common log, is what it's called. It used to be before calculators to do really long multiplication, division, exponential problems. Mathematicians you had to use logarithms. You had to rewrite everything in terms of logarithms. They had to use properties to do this. They had to do huge log tables and lots of work that we now have the luxury of our calculators doing for us. That's why and they used base 10, and that's probably why it's called common law, because they used it so much to do all those heavy-duty calculations. All right, now we get to do evaluating logarithms using mental math. So I've already kind of been working you guys towards this. Here we don't have a base, so it's understood to be log base 10 of 1,000. And we don't know what it equals, so we're going to put an x there. And then to do this, we're going to rewrite this as an exponential so that it makes a little more sense to us. So the base is 10, the exponent is x, because all logarithms equal exponents. And we get this. And then we can see, 10 to what power equals 1,000? Well, that's 3. So therefore, x is 3. So that means this equals 3. Now, you don't really have to do all that work. Once you get good at these and really feel familiar with them, you can put a little 10 in here. You can just think to yourself, 10 to what power equals 1,000? And you can just come up with it right off the top of your head. Okay, this one's a little harder to do. We'll go and do it the same way I did the other one. Make it equal to x. So let's write it as an exponential. The base is 4, the exponent is x, and it equals 1/4. Okay, so 4 to what power is going to be 1/4? Well, I've got a reciprocal over there on the other side, so I know in order to get a reciprocal, I'm going to need that x to be negative. So 4 to -1 would give me 1/4 to the positive 1, right? Which is 1/4. So x is -1. So the answer, here I'll just erase. The answer is -1. So again, you're asking yourself, 4 to what power equals 1/4? The answer is -1. Look at this. I've got a whole page of them, because I love these things. I think they're fun. Hopefully you guys will too. What I would like you to do is do these on your own, and then watch the video, and I'll do them for you. Okay, so this one is 10, log base 10, it's understood. 10 to what power equals this thing? So I'll go ahead and we'll just write it out. 10 to what power equals 0.00001? Well, this is obviously a small number, so it's going to have a negative exponent. And we need to see how many decimal places we have. 1, 2, 3, 4, 5. So 10 to the -5th would be our answer on that one. Okay. Then we are going to do, where's B at? Over here, where's B? So the answer is -5. It's not 10 to the -5, by the way. It's x equals -5. Or in other words, this whole thing equals -5. Because logarithms are exponents. Just the exponent is the answer to the logarithm. Okay, x. So 25 to what power equals 0.04? Well, maybe I need to rewrite 0.04 as a fraction. 4 100ths, how about? Okay, I can reduce that. That's 1/25. No, now I'm getting somewhere. So 25 to the x is 1/25. Okay, I've got a reciprocal over here. I know that that x has to be negative, and it's simply 25, so that means it must be 25 to the -1 equals 1/25. That means the answer to this problem is simply -1, because it's the exponent. So the answer is -1, not 25 to the -1. It's just the exponent that's the answer. Now, hopefully some of those two were kind of hard. This one, you can get to a point where you can do this in your head, because it's going to be 3 to what power equals 27. That's what log base 3 of 27 means. 3 to what power equals 27? Well, that's 3. So you can write equals 3. I think we need a new color. Let's do lavender. Okay, what's the base on this one? 10. So you ask yourself, 10 to what power? So 10 to what power equals 100,000? Well, 100,000 has 1, 2, 3, 4, 5 zeros, so it's going to be 5. 10 to the 5th is 100,000. Notice when I'm counting over, when I'm doing these, I'm going over, I'm starting here, of course, because that's where the decimal is. I'm going over until I get to 1. 1, 2, 3, 4, 5. See how I'm at 1? And then on this one up here, I started at here, and I had to go 1, 2, 3, 4, 5 until I got to this, till it was 1. So you're moving your decimal over until you get 1. 7 to what power equals 49? 2. 4 to what power equals 64? Well, you might have to think about that one. It is 3, because 4 times 4 is 16, and then 16 times 4 is 64. 8 to what power is 64? That would be 2. Fantastic. See how fast they are once you can visualize them? All right, we're going to stop there. We'll do this next little bit as our part 2.